All right, let's go ahead and get started. So this is section 2.7, and what we're going to be looking at in this section is what's called equivalent statements. So when we're working with truth tables and we symbolize a statement, and that's fine. But there's some concern that maybe there's more than one way to get this, to get at a truth table. Okay. So in English, we have lots of different ways of saying the same thing, and because we have such a variety of words, what we're going to look at in this section is what statements are equivalent to each other, okay, which would have the same truth table, and which ones would not. And when we're working in logic, we can always replace one statement with anything that's equivalent to it. All right, so let's go ahead and look at some examples to illustrate what we're talking about here. So here's two statements. The first one is, it is not the case that Alice does not know how to juggle. Okay. The second statement, Alice knows how to juggle. Okay. So if we were to write these down and symbolize them, okay, for the first statement, I could say, all right, the simple statement here is P. And remember, when we make our simple statements, we want to make sure that they are positive, right? So, we want to, if I'm going to write down P, I'm not going to use the nots in there. Okay. So then our simple statement would be that Alice knows how to juggle. Okay. So the first one would be, well, Alice does not know how to juggle is not P, and it is not the case tells me there's another not there. Okay. So we have not P. And the second statement is just P. Okay. This first statement is something that we call a double negative. Okay. And you may have heard that, double negative statements cancel out to be a positive statement. Okay, so it's not the case that Alice does not know how to juggle is the same as saying that Alice knows how to juggle, right? If we were to look at this with a truth table, then it's easy to see, oh yeah, this is the case, right? If I take a statement P, it can be either true or false. Not P has the opposite truth values. Then not P is like taking not P and throwing a not on there, so it has the opposite truth values from not P, which are the same truth values as the original statement P. Okay, so then we can see, oh yeah, it's the same as P, right? So we notice that P and not P have the same truth value in every row. Okay, so statements like this are called equivalent. Right. So when we're working in logic, right, it's going to be important to know what equivalent statements are. So, with simple statements and with double negatives, that's probably pretty simple. That's why we started with this example, okay? Because this is something that you've probably already run into and explored, and okay, a double negative is the same as the positive statement. Okay? But we're going to look at some compound statements that are equivalent. Okay, so two compound statements are equivalent if they have the same truth value, no matter what the truth values of the simple statements are. Okay, so remember, with a compound statement, we're putting them together with like ands and ors and if-thens and so on. Okay, and if two statements give you the same identical truth value, right, same truth value in every single row, then they're going to be equivalent. Okay. So we can recognize by seeing that every row in a truth table is the same. Okay, and equivalent statements are going to be represented, or we'll indicate them with this triple bar equal sign. Okay, so that's going to tell me that two things are equivalent. It's not the same as equals, because they're not the same statement. They're not equal, but they are equivalent. They have the same truth values. So it's like a form of equal almost. Okay, so we have just shown that not P is equivalent to P. So we could write this in logic by saying not P triple bar, which means is equivalent to P. Okay, and just like the equals sign, the equivalent symbol can be used in either order. So you could also write P is equivalent to not P. Okay. All right, so let's go ahead and look at things that are not equivalent. I think sometimes it's helpful if we talk about what something isn't, then it's helpful to understand what it is. So how do we recognize when statements are not equivalent? So let's use a truth table to show that these two statements that we have written here are not equivalent. So here, if I look at not P or Q, and here we have not P or not Q. Okay. So if we're going to set up our truth table, we want to have our basic statements to begin with. So we're going to write P and Q. And then what we're going to do is we want to combine things to be able to get at these compound statements. And we want to combine things one step at a time. Okay. So if I want to create this left-hand one, I need to have a P or Q, and then in a later step, I'll throw a not on there. So we'll say, okay, I'm going to find a P or Q statement. Okay, and then I can throw a not on there so that I'm only doing one step at a time. Okay. And then if I want to create the statement on the right, I need to have a not P column and a not Q column. And then I can combine those two together using OR in order to get my final statement. Okay. So this is the setup for our truth table. And I think that organizing what you have to do is usually the harder part of filling out a truth table. Okay. And then we'll go ahead and fill in the truth values. The P and Q, I like to use the same pattern every time if we have just two statements, right? So true, true, false, false, true, false, true, false. Okay. And then when we're filling out our truth table, it's, I think, helpful to have maybe your little reference card handy. Remember, for the OR statement, if either one of them is true, the OR statement is true. So true or true gives me a true, at least one true gives me a true, at least one true gives me a true. When they're both false, the OR statement is false. Okay. And then here we're taking our column that we just made and negating it, right? We're throwing a not on there. So we're just going to flip all of the truth values. So false, 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 true. Okay. Here I'm going to take the P column and negate the truth values, right? Flip all the truth values. So I'm going to get false, false, true, true. I'm going to do the same thing to Q, flip the truth values. So false, true, false, true. And for our final column, I'm going to take these two columns that we just created, the not P and the not Q, and join them with an OR. So if either one is true, I get a true. When they're both false, I get a false. Okay, so here I have at least one true, here I have at least one true, and here they're both true. Okay, so what we want to do to show that these two are not the same is we want to look at the relevant rows here, right? Okay, so I'm going to start by highlighting the columns that we're interested in, right? So this was our statement on the left, and this was our statement on the right, right? Okay. So if I highlight them, then we can make our comparison, and I can see in the first row, they do match up. But in the second row, okay, when P is true and Q is false, that's what the second row is, right? So we're just kind of being really clear about which row we have. Then our not wait a minute, I think we have a typo here. This should be not P or Q. The not P or Q is false, but the not P or not Q is true. Okay. And in the third row, which is where P is false and Q is true, right, in my third row, again, they don't match, right? So the not P or Q is false, the not P or not Q is true. Okay, since these two statements have different truth values in these rows, they are not equivalent. Okay, so if we want to determine if two statements are equivalent, here's our steps. We create a truth table for each statement, and then we check to see whether the truth values are all the same in every single row. If they are all the same, they're equivalent. If any row is not the same for the two, then they're not equivalent. Okay. Okay, so let's talk a little bit about symmetry. A conjunction, remember, was our and statement. We had more than one word for it, but I think and is our most common one. The symbol, right, was the arrow pointing up. Okay. It's true when both statements are true. Okay. A disjunction, which is the or statement, right, with the symbol arrow pointing down, is false when both statements are false. Okay. The biconditional, which is if and only if, which is symbolized with the double arrow, is true when the statements have the same truth value. Okay, so that means for all three of these, if we switch the order of the statements, we get an equivalent statement. Okay. So if I look at P and Q, it's true when both statements are true and false otherwise. That's not very good looking, false. Okay, so in that first row, they're both true, and then all the other ones, they're not both true. I have, one or more falses. So Q and P is going to be the same thing. When they're both true, I get a true, and if I don't have them both true, I get a false. Okay, so I have the same truth values, so I can see that they're equivalent, right? So the order doesn't matter. The same thing with the or statement. The or statement is going to be false when both statements are false, okay, and true otherwise. So when I have two falses, the or statement is false and it's true otherwise. But for Q or P, I'm looking at the same two rows. When they're both false, I get a false and it's true otherwise. Okay, so I get the exact same truth values. Okay, for P, if and only if Q, when they match, so both trues, both falses, right? Then the if and only if is true. When they don't match, I get a false. Okay. But talking about whether they match or not, it doesn't matter which one comes first, right? So here, Q and P match. Here, Q and P match. And here they don't match. Okay. So we can see with the truth table, the symmetry of three of our connectors. Okay. So because of symmetry, we have that P and Q is equivalent to Q and P. P or Q is equivalent to Q or P. P if and only if Q is equivalent to Q if and only if P. Okay. Now let's look at our other connective, the conditional statement. Right. This is the if-then. Right. So the if-then statement, which is represented by a single arrow, is false when the first statement is true and the second is false. Okay. So here the order matters, right? If we switch the order, we're going to switch which one is first and which one is second. Okay. So if I say if P then Q, here the first statement is true and the second is false, so I get a false and it's true otherwise. But if I say if Q then P, now Q becomes the first statement. So it's in this third row that the first statement is true and the second statement is false. Okay. And there's no other rows where the first statement is true and the second one is false, so these are all true. Okay. So we notice here in the truth tables that the second and third lines or rows are different. So these expressions are not equivalent. So we could say if P then Q is not equivalent to if Q then P. Okay. All right, now we're going to build up and talk about something called De Morgan's laws. Okay. De Morgan's laws are not very complicated. What we want to do is look at how to negate an and statement and how to negate an or statement. That's really all they are. Okay. So when we looked at the negation of P or Q, we saw it's not equivalent to not P or not Q. So what is it equivalent to, right? So what we want to do is find a statement that doesn't include any parentheses that's equivalent to not P or Q. Okay. So we're going to start by creating a truth table for this statement. Okay. So here we have a basic truth table set up, right? We have our symbol statements P and Q with our starting truth values. Okay. So P or Q, remember, is going to be false when they're both false, and true if I have any trues. So these three are true. And not P or Q, I'm going to just take my column that we've just created and flip all of the truth values. Okay, so this statement is true in just one row, right? All right, what do we see in our basic statements? So here's our basic statements and their truth values, right? We've looked at these a bunch of times, so we're not going to bother filling them out right now. What we want to do is we're looking for something that's equivalent to this, right? And this is true in just one row, so we're going to start off there. So let's look at what's true in one row. Well, P and Q. So statement true in just one row is P and Q, right? Or the conjunction. Okay. Statements that are true in two rows, that's the if and only if. Or biconditional. Okay. The other statements, the or statement and the if-then statement, are true in three rows. Okay, so the disjunction and the conditional are true in three rows. Okay, so if we want to find something that's true in one row, it looks like that we're going to need an and statement. Okay. But it's not quite going to just work like that. Here, the thing that I want to be equivalent to, the one true that we have is in the bottom. For the and statement, the true is in the top row. Okay. So what we're going to do is we're going to use some negations to sort of control where that true line appears, that one line that's true. Okay, so let's look at our truth table with some negations in it. Okay. All right. So what I want to do is I'm going to look up a bunch of different combinations, right? We're going to look at P and Q. We'll throw one negation in there, not P and Q. We'll throw the negation on the second one, P and not Q. Throw a negation on both, not P and not Q. Remember, these are, the and is symmetric, so we don't need to have any of them start with Q because it would give me the same thing. Okay, so now let's fill out the truth values. Remember, the and statement will be true when they're both true and false otherwise. So here I have P true, Q true, so I get true, and then at least one false on the other three. Okay, now we're going to look at the not P and the Q columns, so these two. Okay, so I have at least one false, both false, double true, and at least one false. So I get my true on this third row. Okay, P and not Q, right? So I'm looking at these two. Here I have at least one false. In the second row, they're both true, both false, at least one false. Okay. So our true is on the second row. And then finally, not P and not Q, right? Both false gives me a false. At least one false gives me a false. At least one false gives me a false. And on the fourth row, they're both true, so I get a true. Okay, remember that what we wanted was only one true on that fourth row, and that's what we see here. So our truth table matches the not P and not Q. So this gives us that our original thing, right, not P or Q, has the same truth table as not P and not Q. So this gives us that not P or Q is equivalent to not P and not Q. Okay. All right. So this is one of the two equivalencies that is De Morgan's laws, right? So here's De Morgan's laws. For two statements P and Q, we have the following equivalencies. The first one we just came up with, not P or Q, is equivalent to not P and not Q. The second equivalency is if we just flip things, right? If I wanted to look at the and statement instead, not P and Q is equivalent to, and if we test all the or statements out, we'll find not P or not Q. Okay, so we're not going to go through this second one in our notes right now. All right, well, let's look at conditionals and disjunctions. Okay, so when we're using truth tables to symbolize a statement, okay, and specifically when we're looking for equivalent statements, okay, we need to deal with the fact that we have two basic statements that are true in 3 rows. Okay. Okay. So a disjunction, remember that's the or statement. Okay, oops, the arrow pointing down, is true except when both statements are false. Okay, so it's going to be true in 3 rows, right? The only time it's false is when they're both false. A conditional statement, okay, that's the if-then statement, right, symbolized with the arrow, is true except when the first statement is true and the second is false. Okay, so that's the only row where it's going to be false. So it's true in the other 3 rows. All right, when we're symbolizing a statement, like how do we decide which one to use, right? So in symbolizing a statement, okay, if I'm looking for something that's equivalent to something that has 3 true rows, I can either use an or I can use an if-then, because both of them are true in 3 rows. And as we saw a minute ago, by messing around with a bunch of knots, you can kind of control where your, we saw when we had one true, we can control where that one true is, right? Well, similarly here, by using the combinations of knots, I can control where that one false statement is. Okay. However, we're going to prefer the or statement if we had a choice between the two, because it's easier to work with. Okay, the if-then statement, okay, it's not symmetric, it can be confusing. Okay, so if I can pick one or the other, and they're both equivalent, we're going to default to the or statement. Okay, if our original statement was symmetric, it's an and, an or, and an if and only if, we'll look for an or equivalent because it's also symmetric. If our original statement is a conditional, well, that's when we're going to look for a conditional statement. Okay. Maybe not always, but But if it's going to be, easy to do, we started with a conditional, then we'll stick with a conditional. But we could pick whatever we want. Okay, let me explain what I mean by looking at our truth tables here. Okay, so what we're going to do is we're going to look at the possibilities for an or statement where we include, a not P and a not Q, or some combination of them. Okay, so for the or statement, remember that it's going to be false when both are false. Okay, so P and Q are both false, and true otherwise. If I have one or more trues, then it's true. Okay, so for not P or Q, so I'm looking at these two. I can see in the second row they're both false, and in all the other rows I have at least one true. Okay, P or not Q. Okay, so this is, these two on the ends. I can see here in the third row they're both false, and in all of the other rows I have at least one true. Okay, the not P or not Q, it's the very first row that they're both false, okay, and true in the other ones. All right, so you can see that by messing around with the my original statements, by throwing nots in there, we can control where that one false goes. First, second, third, or fourth. Okay. So let's look at the if-thens. The if-then, if I want to be very careful and look at all the possibilities, we need to look at the ones where we have P first and Q second, and then also the ones where we have Q first and P second. Okay, because it's not symmetric. So let's go ahead and look at those. So if P then Q, so remember that the only time it's false is if we have the first one is true and the second one is false. Okay, for all the other ones, the if then is true. Okay, so if I start with a not P, and my second one is a Q, so first is true, second is false, happens on the fourth row here. So all the other ones are true. Okay. If P then not Q, right, so we're looking at these two. First one is true and the second one is false. We get that in the first row. Okay, true then true, starting with false. These are going to all give me a true conditional. Okay, then finally, if not P, then not Q. Okay, remember we're looking for if true, then false. That's where we get a false. And if then that starts with a false is always true. And if true, then true is also true. Okay. So we can see, all right, I don't really need to reverse the order to be able to have a false in any one of the four spots, right? We can see, all right, here it's the first row, second row, third row, fourth row. Okay. If we do reverse the order, though, right, let's take a look at that. If Q, then P. So Q is my first statement. So if true, then false happens on my third row here. So that one's false, the others are all true. Okay. If not Q, okay, so my not Q is going to be my first statement, then P. So starting with a false will give me a true. If true, then true gives me a true. Starting with a false gives me a true. If true, then false happens on the fourth row, so that's where I get my false. Okay. If Q, then not P. If true, then false happens on the first row. Okay, starting with a false gives me true conditional. If true, then true gives me true. And starting with false gives me true. Okay. And finally, if not Q, then not P. The not Q is the first one. Okay, So starting with a false gives me true. If true, then false, right? My first one is true, and my second statement is false. That's when the conditional gives me a false. And the other ones are going to make the conditional true. Okay. All right. So the or statement, by messing around with the nots, I can get 3 trues and a false in any order I like. The if then, where the P is first, by messing around with the nots, I can get 3 trues and a false with the false in any spot I like. Conditional, where the Q is first, by messing around with the knots, I can get 3 trues and a false, where the false is in any spot I like. Okay, so I can say that P or Q, that's where the false is in the 4th row, is going to be equivalent to this one, because I have the same truth table, right? The false in the 4th row, the others are true. So P or Q is equivalent to, if not P, then Q. And if I look down here, I get a false on the 4th row when I have, if not Q, then P. Okay. If I look at my second or statement, the false is in the 2nd row. I get a false in the 2nd row when we have if P, then Q. I get a false in the 2nd row when I have if not Q, then not P. Okay, so these are equivalent, right? When I start with not P or Q, that's equivalent to if P, then Q, which is equivalent to if not Q, then not P. All right. Third or statement has the false in the 3rd spot. If not P, then not Q has a false in the 3rd spot. Okay. If Q, then P has a false in the 3rd spot. So these 3 are equivalent. And finally, not P or not Q has a false in the 1st spot. If P, then not Q has a false in the 1st spot. If Q, then not P has a false in the 1st spot. Okay. So we have a bunch of equivalencies here. All right, let's make a little bit of use of these. We're going to go somewhere with this. Equivalence to conditionals, okay? We can see that with the use of negation, we can write an equivalent to any conditional that uses a disjunction. Okay. So what is the equivalent to if P, then Q? Okay. So I can do this using a truth table, right? I could also just cheat and look up here. Say if P, then Q, we already showed was equivalent to not P or Q. That's cheating. Let's go ahead and fill out a truth table. Let's figure out which one it is. All right. So I'm going to look at my basic statements, P and Q. I'm going to look at if P, then Q, and I have my basic truth table for that. It's false when I have true for the first one and false for the second, and true otherwise. Okay. We set up a not P column and a not Q column. So now let's fill out all of the possible or statements. So P or Q, it's going to be false when they're both false, and true if I have to, oops. That's crazy. True if I have at least one true. Okay. Not P or Q. So here's my not P column. Here's my Q column. I have both false in the second row and at least one true in all of the other ones. Okay, P or not Q. So I have at least one true, at least one true, false, and then not Q is also false, so they're both false here, so I get a false, and then at least one true. Okay. Not P or not Q, they're both false in this first row, and at least one true in the others. Okay, so I can see that this one, false in the second row, matches this one, false in the second row. So this is a conditional exchange. If I have a statement if P then Q, I can say that's equivalent to not P or Q. So I could switch out any if then statement with an or statement. Okay. So here's another way to look at that. Let's look at some English sentences. So let's look at this if then statement. I will cook dinner only if I have enough time. We're going to rephrase this as a disjunction or statement. Okay. So let's look at our simple statements. First statement, I will cook dinner. Okay. Our next statement, I have enough time. Okay. Remember that only if was backwards to if, right? So if P then Q is the same as saying P only if Q. Okay, so we talked about that when we first introduced the conditional, and we looked at the different ways of writing it that were the same. Okay, so here we have to be a little bit careful. The only if can be tricky. So this, when I symbolize it, is the same as this statement, if P then Q. We just said a second ago that that's equivalent to not P or Q. So I can write that in words. Not P, I will not cook dinner. Okay. Or Q, I have enough time. Okay. A way that we would more commonly see this written in English, I don't think I've ever heard somebody say the words, I will not cook dinner or I have enough time. A way that would be maybe more common to phrase this would be, I will not cook dinner unless I have enough time. Okay, and that is something that you would, I think, hear an actual person say. Okay, so this is the process of taking a conditional statement and turning it into a disjunction, right? Or just taking that if then and converting it into an or statement. Okay. All right, now let's look at which conditionals are equivalent to each other. So with the use of negation, we can write an equivalent to any conditional that uses the reverse order. Okay. Now, that doesn't mean that we can just reverse the order. We know that if Q then P is not equivalent to if P then Q. That was one of the first things that we discussed, was that the if then statement is not symmetric. Okay. What is equivalent to if P then Q? Okay. So what we're going to do is we're going to look at using negations, and we're going to look at with Q first, which one is the same as if P then Q. Okay, so remember, with an if-then statement, it's false when our first piece is true and the second one is false. That's when we, broke our promise. Okay. So if my first one is true, so here I have a true and the second one is false. No, didn't happen. I don't have the first one true. The first one is true and the second one is false. That's when the if-then is false. Okay, and here's the first one. True. Okay, so we're going to repeat the same thing with different columns now. So starting with the not Q, to get a false, I have to start with a true. Okay, so didn't start with a true, and the third one doesn't start with a true. Okay, so here I start with a true. The P is also true, though. Okay, so I start with a true, and the second one is false, so that's where our if-then is false. Okay, I think that we wanted that these are backwards. I wanted to start with I always want to start with a Q. So we'll do if Q, then not P, and then finally, if not Q, then not P. Okay, a couple of typos. All right, so let's fill out the truth values for this one. Okay, if Q, then not P. So if true, then false. That gives me a false in the first one. And then I start with a false, so I can't get a false. If true, then true. Gives me true. And starting with a false gives me a true. Okay. If not Q, so the not Q is the first one. Right? I start with a false, it's true. If true, then false, that gives me a false. And it's going to be true otherwise. Okay, what we want to do is look at the if P then Q and say which one is equivalent but starting with a Q statement. So here I have a false in the second row. Here I have a false in the second row. So I want if not Q, then not P. So if P then Q is equivalent to if not Q, then not P. Okay. So the statement if not Q, then not P is called the contrapositive of if P, then Q. Okay. All right, and remember these are equivalent. They have the exact same truth values, so the same meaning. So let's look at an example in English. So here's our statement. I will cook dinner only if I have enough time. Okay. Notice it's the same one that we used a minute ago. So my first statement, P, is I will cook dinner. And my statement Q is I have enough time. Okay, except that instead of joining them with an or statement, we're joining them with, well, I think we did the same before, right? I will cook dinner only if I have enough time. So we have the same thing to watch out for. The only if is not the same as the if. Okay, it's like the then piece. Okay, so I will cook dinner is the first one. So this is going to be symbolized as if P then Q, which we just said is equivalent to if not Q then not P. So if I write that out back in English, not Q is I do not have enough time. Okay. Not P is I will not cook dinner. I like to write my if-then statements with an if and a then. So if I'm doing not Q first, I'll write if not Q, then not P. So if I do not have enough time, then I will not cook dinner. Okay. Maybe a more common way to see this written, remember, as long as I have an if on a statement that is going to be the same, let's change the phrasing so that we put this second part first. So I will not cook dinner. If, so I'm going to put the if on the I do not have enough time. Okay. So I will cook dinner only if I have enough time is the same as saying I will not cook dinner if I do not have enough time. Okay, they're logically equivalent. Okay. Let's look at some conditionals and biconditionals, starting with two simple statements. So statement P, Kyle will go for a walk every day. Statement Q, Kyle has a dog. So there are two conditional statements and one biconditional statement that we can form from these statements. There's only one biconditional because the biconditional is symmetric, so it doesn't matter which one we put first. So the conditional statement, if P then Q, would be if Kyle will go for a walk every day, then Kyle has a dog. Or another way to phrase that would be Kyle will go for a walk every day. Only if, because that's like the then, right? He has a dog. Okay. If Q then P, if Kyle has a dog, then he will go for a walk every day. Okay. I'm just going to choose to switch the order. So it's if Kyle has a dog, then he will go for a walk every day. I'm going to put the if he has a dog as the second part. Okay. Okay. The then part was Kyle will go for a walk every day. I didn't leave myself enough room. Okay. And then the if and only if, Kyle will go for a walk every day if and only if he has a dog. Okay. What I want to do is look at the connection between our conditionals and the biconditional. Okay. The biconditional, the language we use is if and only if. Okay. Well, if I start with Kyle will go for a walk every day, only if is one direction of the conditional. If is the other direction of the conditional. So if and only if kind of in the language tells us that it's going to be this conditional and this conditional. Okay. So this suggests a relationship between two conditionals and the biconditional. For any statements P and Q, P if and only if Q is equivalent to P only if Q, and the way to flip this would be to say if P then Q. Right? So we have if P then Q and P only if Q. All right, so let's verify this using a truth table. All right, so the idea is that the biconditional is just two conditionals connected with an and. All right, so let's look at this with a truth table and make sure that what we think is right is actually right. So my truth table for P if and only if Q, if they match, we get a true. So two trues match, two falses match. When we get a mix, they don't match, so it's false. Okay. If P then Q, I know that if I have an if true then false, I get a false, and it's true in all of the other cases. If Q then P, if I start with a true and then get a false, I get the conditional is false, and it's true in all the other cases. So now let's take these two columns and join them with an and. When they're both true, the and statement is true. If I have at least one false, the and statement is false. At least one false, the and statement is false. Here they're both true, so the and statement is true. Okay. So you can see with our truth table that P if and only if Q really is logically equivalent to if P then Q and if Q then P. Or another way of saying it would be if P then Q and P only if Q. Okay, so we get the if and only if. All right, so let's kind of summarize all of this stuff that we have so far. And this will be maybe a nice reference sheet to look at, you know, for equivalent statements. Okay, so this isn't every equivalent statement, right? There's no end. There's infinitely many equivalent statements that you could come up with. But these are really common ones. So like the double negation we started with, right? A double negative is equivalent to the original statement. Okay. The contrapositive is a very common one. Okay. The De Morgan's laws, conditional exchange, conditional negation. So these are all things, for the most part, that we proved today, right? Some of these we haven't, and the ones that we haven't are going to be in your homework. Okay. We also talked about symmetry a little bit. The and, the or, and the biconditional statement are symmetric. So when you change the order, you get the same thing. So those are automatically equivalent. Okay. And you know, we didn't look at a truth table to do that. We could just say, yeah, when we're doing a truth table, it doesn't matter which one comes first. So okay, thanks. But I think that we're all good anyway. So this is our last page of like summarizing equivalent statements. Okay, so I'll post up homework about this. And I think in doing your homework, you know, you can certainly use this as a reference sheet. But for a lot of the homework, you're going to have to, you know, suppose you wanted to prove this one, right? Show that this P and Q, or sorry, if P and Q then R is equivalent to if P then if Q then R. Okay? In order to show that, what you need to do is you need to construct a truth table. Okay, so we'll start with statements P, Q, R. That's a truth table with 3 simple statements, so it'll have 8 rows. Okay, and then you just want to start by finding the things in parentheses and creating a column for those. And then you can create a column for the more complicated things by joining things that you already have with a single connective. you know, kind of like the way that we did, you know, going through here when we were proving some of these other ones. Okay, so this is a good reference sheet, but for the homework you're going to be doing, you're going to be proving some of these. So you're going to be creating truth tables. Right? And we'll maybe have a day where we go through and answer homework questions before it's due. All right, any questions?